should see Chapter 5, Quiz 1. Again, let me know if you can't, because sometimes I'm clicking the wrong buttons. All right, so this is our first force analysis problem. So this is a major category we're stepping into. We're going to use force analysis method. Chapters 2 and chapters 4, we use kinematics analysis method. And then in chapters 7 and 8, we're going to use energy analysis method. And it's not like once we're done with chapter 8 that you don't see these again. You see them throughout. These are threaded throughout everything in physics and in engineering. So very foundational stuff. If you look at your green sheets, let me pull up my copy. If I look at my green sheets under force analysis, you should have this handout. This is a big part of what we're going to do right here that you see on the screen. This is the methodology. I mean, there's a lot of fine print here. Don't worry, I'm not going to read through the fine print. You can read through the fine print, but I will literally starting today, we'll start hitting on all these categories. And again, here's the bargain. Here's the bargain I'm offering you. In return for learning this startup process, for spending a pretty decent amount of time and effort learning this methodology, in return, you're going to do better. You're going to understand things better, deeper, quicker. You're going to do better on the exam. It's why if you end up in a job within STEM, science, technology, engineering, math, you're all about methodologies. There's a reason why we reuse best practices. So I'm just going to keep that there. Well, that's kind of taking up a bunch of room. So here's our first question, first challenge. We have an overhead view of a lemon half. So the author likes to use fun references when referring to a object. So this is a lemon half. So we're looking at, this is a top-down view. We're looking at this from a top-down view, and we see two of the three forces. There are three forces, F1, F2, and then it says, in unit vector notation, what is the third force if the lemon half is supposed to be stationary? So there is a third force, and right now I don't know anything about this third force, so I'm just going to draw it. I don't even know what quadrant to draw it in. I'm just going to say, okay, there's my third force. I'm drawing it in quadrant 1. It might not be in quadrant 1, but this is just a preliminary guess. I am guessing that there is a third force somewhere that when you combine force F1, F2, and F3, when you combine them, that lemon half, this object, remains stationary. So there's a ton of component forces, but when you blend the forces together, the result is no acceleration whatsoever. It starts at rest. It stays at rest. So here's the first of the great introductions. Let's do an XY force table. So this is typical. There's quite a bit of setup to do, but it's worth it. You know, there's a tendency. I have a tendency to I just want to start doing equations. Like right now, I just feel the urge just to start writing down equations. I don't want to spend any time setting things up. I don't need that, but that's a lesson I've learned that, yeah, it does pay huge dividends to go through a big setup phase. So here's the setup phase. Let's do, let's call it a name. So and you're going to do this on exam. Yeah, you're going to do this on exam 1. So the sooner you acclimate yourself to these methods, the sooner you're going to do well the better you're going to do on the exam, because again, I will ask you, I'll say, provide an XY force table. And here's the XY force table. Name, vector. You don't have to memorize this table. You can look it up. X and Y. This is the force table. So let's talk about the names. All right, here's a vector. This is vector F1. I have vector F1, which is given. I have vector F2, which is also given. I have vector F3, which I don't know anything about. I need to find out about F3. And ultimately, I have the net result of all of these vectors acting together, F net, which looks like 0. It's a 0 vector. So here's the table. Well, let me just keep going with this. All right, so the thinking is, if I add up all of these vectors, F1 plus F2 plus F3 equals the net vector. So I could literally indicate it like this. The net vector acting on that lemon is the vector sum of F1 plus F2 plus F3. So that's all we're doing here. I mean, it's really kind of, it's that obvious. So now let's kind of peel apart the layers. And before I dive into it, I actually have to remind us all, maybe you don't need reminding, of the unit circle. The glory of the unit circle. Here's a unit circle. You have no idea how helpful it is to be familiar with the unit circle. In fact, I don't even remember when I learned the unit circle. I think I first learned about the unit circle in 1949 or so. It's been a while. I might, and I think I'm still pretty sharp as far as the unit circle is concerned, just because it's you can't help but use it a ton of times. So the unit circle basically says this. It says this is a circle, and if you have a point, say there on this unit circle, and let's say this point makes an angle theta, like this, with respect to the origin. So this is angle theta, and this has a radius of 1. So unit circle means the radius is equal to 1. The radius is 1 everywhere. It's just a unit circle with a radius of 1. And this is the big takeaway right now. What is sine? Sine corresponds to this dimension right here. So I'm indicating this dimension right here. This value is sine theta. Cosine is indicated right here. I do a straight vertical down to the x-axis. So this dimension, this value right here is cosine theta. That looks good. So cosine theta refers to this position along the x-axis. Sine theta refers to this position on the y-axis. And I guess that's it for the unit circle. Maybe there's more, and this is where you're getting sine squared theta plus cos squared theta equals 1. So that's good. All right, so now what I'm going to do with that as a reference, going back literally, I think, to day 1 of this class. I think this happened on day 1. In your green sheets, there is mention that says, let's use, in terms of for angles, let's just use this as the standard convention for angles. Let's measure angles as going counterclockwise with respect to the plus x-axis. And that is a good idea. I mean, sometimes we're going to ignore that advice, but this is really helpful advice most of the time. So here's what I'm going to do. For F1, let's draw an angle for F1. F1 right here. Let's just refer to this as angle. Let's refer to this as angle A. So I'm kind of ignoring their theta 1, and I'm saying, hey, I'm going to stick to this convention. You know why? Because I'm an engineer and I like nice, logical, rational processes and repeatable approaches. So I'm going to stick to this. I'm going to call the angle to F2 angle B. So let's do that, indicate that. Now, going counterclockwise with respect to the plus x-axis. So again, notice, you guys, I'll do this again. I'm starting at the positive x-axis and I'm drawing counterclockwise like this. So this is me going counterclockwise from the plus x-axis. I'm going to call that angle B. Last but not least, I'm going to once again start at the positive x-axis and go counterclockwise and call that angle C. So I'm doing that because that's a convention, and you will see that it makes sense to do this. Angle A, let's just write values. Angle A equals, for me, using my numbers, angle A is going to be 180 minus theta 1, and my theta 1 is 29. So my angle A, you make sure you get your angle A. My angle A is 151 degrees. My angle B is, according to my visual, it's going to be 270 plus theta 2, which is 32, or 302. Angle C is, I don't know. Angle C right now is a $sign. So that's it. That's this is me setting up my XY force table, which again, on exam one, it'd say, hey, using one or more XY force tables, go ahead and figure this out. All right, so let's talk about the X component of F1. Well, first of all, F1 is looking like, here's F1 according to the given diagram. For me, F1 is going, F1 is looking like this. That's F1. So you know what I'm going to do? The X component. Here's the X component that I need to capture. This is the X component.
Professor, you said that A equals 180 minus theta, or I heard
180 minus theta 1 right here.
Oh, okay, got it.
Okay. Yeah, this is the theta 1. Right. Good question. So I need to capture that X component, and then I need to capture this Y component like that. Okay. And the angle I'm using, here's my angle A again, just for the sake of completeness. Angle A is like that. That's angle A. All right. So now this is where it starts to really pay dividends. Here's the X component. The X component is just going to be F1 cosine theta. I'm sorry, F1 cosine A. F1 cosine A, and without even thinking, this is F1 sine A. It's that easy. Because again, cosine, that's why I put up that little unit circle recap. Cosine here is capturing the X component, just like sine, this sine term right here is capturing the Y component. Let's go to F2. F2 is my second vector. F2 is in quadrant 4. So there's F2. Here's angle B. Angle B starts at the plus X axis and goes counterclockwise. So this is angle B. And once again, it's the same methodical approach. I need to find this X component, and I need to find this Y component. And that's what I'm doing via this tabulated approach, this Y component. Okay, so that's done. Ready? This will be F2 cosine theta captures the X component, cosine B specifically, and F2 sine B, F2 sine B captures the Y component. Done with that. F3, I don't know. So right now, F3 is just a question mark, and I'm just going to leave it as F3 cosine angle C, and this will be F3, and I forgot my subscript. That should be a 2. This should be a 1, so sloppy with the subscripts. This will be F3 sine C. That's it. That's it. So all I'm going to do now is add up the X. It's like Humpty Dumpty. I'm going to add up all of the X components. So literally, I'm breaking things down and then putting them back together. But before I put them back together, I'm going to group them. That's what I'm doing right now. I'm going to take all of these X components and add them together. So when I add all of these X components together, I get the following. I get F1 cos A plus F2 cos B plus F3 cos C equals F net. And what is force? F net. Well, here's a reminder. This is really at the heart of chapter 5. More than anything, Chapter 5 is about F equals MA. So if F equals MA and A equals 0, mass times 0, 0 meters per second squared, why is the acceleration equal to 0? Because the lemon half is remaining stationary. So all of this that I'm writing in purple equals 0. So I'm just going to do maybe a few more operational steps. You know what that means? That means F3 cos C equals 0 minus F1 cos A minus F2 cos B, and done. And it gets better. This is F3 cos C, because F3 cos C, let me do a redraw here. If this is my F3 vector, and again, technically I don't know what quadrant it's in, and it doesn't matter. It really doesn't matter. But let's just say for the sake of conversation, this is F3 in quadrant 1. This is angle C from my positive x-axis going counterclockwise. That's angle C. And you need to enter the result. You need to enter F3 in unit vector notation. And I have it in unit vector notation because here's the x component. This is the x component. This is the y component. And again, I better label things. This is my mystery vector. This is F3 vector. This is F3x. F3x. This is F3y. And that's it. And you know, I'm looking right at, because here's another way to write F3y. F3y can be written as F3 j hat. F3x can be written as F3 I hat. Those are the unit vectors. I hat is a unit vector, has a magnitude of 1, it's pointing in the positive x direction. J hat has a magnitude of 1 and it's pointing in the y direction. And I'm done, because if you look at this, you guys, just look at F3 here. This is a right angle triangle. That's 90 degrees. It's a right angle triangle. You get to use SOHCAHTOA and Pythagorean theorem. Look at this triangle right here. If I just said cosine of angle C equals side adjacent F3x all over the hypotenuse F3. So I'm seeing right here F3x, also known as F3 I hat, is expressed as F3 cos theta, cos C, sorry. And you're done. And that's sitting right here. This is your answer. So this is why I'm loving this method. Loving this method. Knowledge is power. Truth is beauty. So let's do 0 minus F1, 8 newtons, times cosine of A, 151, minus F2, my F2 is 11, times cosine of angle B, which for me is 302. And I have my answer already. This is going to equal, this equals 1.167, 1.167 newtons. I'm going to put this in calculator memory location A, store alpha A. So that's the correct answer for the I hat component of F3. Question, what is the J hat component? So that is a job for the Y column. So let's just, this is going to be literally a copy and paste of what we just did. Let me change colors here. Step 3. Step 3 says let's find the Y component, F3Y, which is the same as F3J hat. And then from Y column, from the Y column. Okay, so go ahead, look at the Y column, and let's just add all of these up from here. Maybe I'll do it like the, oh, that's kind of unintended. Okay, from here to here. I'm going to add up all of those Y column entries. And when I do that, I get the following. Just add them up. F1 sine A plus F2 sine B plus F3 sine C equals F net, just like we did with the X column. And that equals 0 because of F equals MA. Right, again, if this is a stationary object, that means there's no acceleration, which means there's no net force. So there you go. Here, and here's your answer. Your answer is right here. Your answer is F3 sine C. For all of the reasons I mentioned, if I go back to this triangle right here, I might, now it's time to say, okay, let's go ahead and take the sine. The sine of angle C is side opposite, which is F3Y over hypotenuse, which is F3. And that's how I'm saying F3Y is represented as F3 times the sine of angle C, because the sine captures the Y component. So this is my answer right here. This is F3Y, which is the same as F3 J hat. So let's solve that and move on. Number 5, solve for F3 sine C. F3 sine C, because F3 sine C is the Y component. And let's do that. F1 angle A, F2 F2 angle B, and we're done. Store alpha B. I get 5.45. 5.45 newtons. Put that in memory location B. Let me do some highlighting here. Let's B this. Oh, this is the answer to A. And this is the answer to A. Okay, and that's it. We are done with A. So this is my answer. This is my I hat component for A. This is my J hat component for A. Done. Done with part A, which was really the heavy lifting. Let's do part B. Part B will take us, I think, 30 seconds to answer. Number 4, 5, 6. Okay, so number 6. For part B. Part B says, what happens if the velocity is constant? If, and here's how I'm going to write constant velocity. If delta V equals 0 means constant velocity. So just introducing that term a few times. Constant velocity means it doesn't change, which means delta V equals 0. Constant velocity. If the velocity is constant, find, once again, F3. And specifically, find the I hat component of F3 and the J hat component of F3. The I hat component refers to the X component. The J hat component refers to the Y component. And number 7, I'm going to see same result. Same result. So that is a very bold comment. Same result. Y Why? Because, go ahead, what were you going to say?
Because acceleration is 0.
That's right. Why is acceleration equal to 0?
Because it's a constant velocity.
Right and right. Correct and correct. Acceleration equals 0 because delta V, acceleration is delta V over delta T, and the problem said the velocity is constant. So we are completely done with part B because it's still, everything's the same. Everything's the same because this is equal, the net velocity was 0 for the X component, and the net velocity is 0 for the Y component. That was true for part A as well as part B. So no change there. However, part C, I think, is going to be a little bit heavier lifting. Okay. I'm on step 8. Step 8 for part C. What's going on? Let's find the I hat component of F3 and the J hat component of F3 if velocity is not constant. For me, I have a velocity equal to 14t I hat minus 16t j hat. So that's for sure not a constant velocity, and I need to find, okay, what's the acceleration? The acceleration is not equal to 0. So this is different. What is the acceleration? And this is where you go back to your green sheets, or maybe you know this already. The x component of acceleration equals dv dx, just using subscripts. I'm sorry, dv dt, the time derivative of the x component of velocity. So it's derivative time. I need to be able to take the time derivative of Vx, and this right here, for me, this is Vx right there. This is Vx. Similarly, this right here, that negative 16t, this is Vy. So I need to take the time derivative of Vx, which is 14t I hat, 14t meters per second I hat. Okay, so this is my a sub x. My a sub x is just simply 14 meters per second squared. That's a sub x. What is then, and then I would say this is net. This is net acceleration. Net acceleration. I better stress, I'm just going to say net AX. So then the net FX is Newton's second law, F equals ma. So if I do mass times acceleration just for the X component, by now you should hopefully be okay with this whole approach of breaking things down into components. My mass is 0.028 kilograms. My X acceleration is the time derivative of the X velocity, which is 14 meters per second squared. This is kg, I hat. So here's my F sub X. It's not 0. It's going to be 0.028 times 14, or 0.392. This is my new A sub X, 0.392 newtons. Let's talk about dimensions, because you're going to have to do dimensional analysis, and it's good. Don't think of dimensional analysis as a chore. Think of it as a great way to give you a heads up on if you're taking a wrong turn somewhere. Right here, I've got kilograms times meters, and then I have a kilogram meter in my numerator. My denominator, I have seconds squared, and a kilogram meter per second squared. This is known as a Newton. 1 Newton. So ideally, you're familiar with that because, again, if you have not watched those lecture videos, if you didn't watch the lecture video yet, you're going to be okay, but you're not getting out of this what you could be getting out of it. It's a difference. It's a real difference to walk into class having pre-sensitize yourself to this material. So that's F sub X. Let's do the same thing. So you know what that is. In terms of I'm going to leave everything in place here, but let me just, I'm going to clear the decks a little bit here and just update this. So I'm going to repurpose this. On the exam, you would basically maybe just draw a whole nother XY table or something that's easy to follow. All right, so F net, the F net for the X component, for me, numerically speaking, is 0.392. This was 0.392 newtons. Yeah, I dimension, I hat, direction. All right, so I've updated my XY force table for part C. I'm going to do the exact same approach to find A sub Y and then F sub Y. So ready? Here goes. A sub Y equals the time derivative of the Y velocity. And for me, I need to take the time derivative of my Y velocity, which was given, as I mentioned, right here. For me, it's negative 16 t I hat. So if I take the derivative of that, it's just going to be negative 16. So I need to do derivative of negative 16 t I hat meters per second. And if I take that derivative, that is in fact negative 16 t. No, sorry, negative 16. Negative 16
Professor?
meters per, yep, question.
Is it not J hat because it's Y?
No, you're right. That's a good catch. You are correct. J hat. Very, very helpful. That's good to hear. J hat. It is J hat because it is Y, and my Y function is negative 16 t J hat. Okay. That's looking good. And similarly, what is the net Y component? I'll write it as Fy net. It's mass times A sub Y because F equals MA. And I'm just separating it based on X or Y. So I need to take the mass, which is 0.026. No, my number is 0.028. 0.028 kilograms times negative 16 meters per second squared J hat. And I am getting an answer when I multiply 0.028 times negative 16, I get negative 0.448. Negative 0.448 newtons in the J hat direction. Correct. All right. And I think I'm going to write that down, negative 0.448. So I'm going to go back up here. And this equals negative 0.448 newtons J hat. Like that. That's it. And now it's business as usual. Now I'm just going to add up the X column. Okay, I'm going to add up the X column. Let me zoom out and proceed just like we did before. Okay, X column. So I'm on step 14, changing colors. All right, so step 14 says add up X. Add up X column. Here's what I get. I get F1 cosine A plus F2 cosine B plus F3 cosine C equals 0.392 newtons. And this is what you're solving for. You are solving for F3 cos C right here. This is the X component for reasons that I hopefully clearly revealed before. I'm just going to make sure this equals F3 I hat, also known as F3 X. So let's get an answer right now for F3 I hat, because it's staring right at us in step 16. 0.392 minus F1, which is 8 times cosine of 151 minus F2, which is 11 times cosine of angle B, which is 302. And I guess that's it. 1.5. Let me redo. I got the right answer. So I'm just off a little bit. Let's see. 0.392. Let me double check something. 0.028 times 16,448. Oh, that's my mistake. That's my mistake. No, that's not my mistake. I'm good. I'm good on that. 0.392. Okay, I'm good. 0.028 times 14. That is 0.392 minus F1. 8 times cosine A, 151, minus F2, 11 times cosine of B, 302, 1.16. Actually, hang on. I'm getting a wrong answer. Let me, F1A plus F2B plus F3C equals 0.392. I'm doing something stupid.
Wait, what's your number coming up as?
Different than what I have on the screen. Did you get the right answer?
I haven't plugged mine in yet, but I know I had it wrong first because I entered it wrong. Came like 17 something. So
Yeah, I'm just messing up on some basics here. So F1, 8 times cosine of A, 151, minus F2, which is 11 times cosine of B, which is 302. Oh, shoot. I had it right all along. I was looking at the wrong slot. I had this answer right all along, but I was looking at the wrong area. I get F, and I was wondering, how hard can this be? How hard can like 7th grade algebra be? F3, and the answer is pretty hard sometimes. F3 cos C, that is my answer. My calculator is saying 1.56. 1.5, yeah, when I round. All right, newtons. That's the answer. That's the answer for the X component for part C. And it's going to be the exact same approach for the Y component, changing colors, 16, 17. Let's add up the Y column. If I add up the Y column, this is what happens when I add up the Y column. I get F1 sine A plus F2 sine B plus F3 sine C equals the net force, the net Y dimension force, which is negative 0.448. Negative 0.448 newtons. And this, you are looking at the Y component of F3, right here. The sign will capture the Y component. So this is F3 J hat also known as F3Y. That's that. So let's solve for that and be done with this problem. Our very first force analysis problem. Okay, so F3 sine of C equals negative 0.448 minus 8 times sine of A minus F2, which is 11 times sine of B, or 5 exactly, almost exactly 5, very close to 5, equals 5 newtons J hat. And that is also the answer to part C. So that's the answer to part C. This was the answer to part C. Okay. So done. Again, this is part C I hat component. This is part C J hat component. This was part A. I guess I did erase it, I think, for part A. All right, but yeah, that's it then. We're done. I was going to circle the results for part A and B, but I just now realized I erased it. So that's good. Your job is to continue to point out my mistakes and to ask questions if there's anything less than clear. And while you're, give me another minute from now to start up Chapter 5, Quiz 2. So we'll do this. We'll do another problem, and then we'll take a break. So if you're still wanting to catch up with any of these quizzes, you can do it over the break, or again, I'll leave some time at the end of class. So nobody's going to run out of time. The only way you don't get these quiz questions correct is because you don't speak up and ask for help or an extension. So we're ready for Chapter 5, Quiz 2, which is already available. All right.
I'm not sure when the deadline for this one is, but my Wiley Plus the free trial ended, so I was like putting that back, or I paid for it right now, so I'm kind of catching up, but I might need some extension time at the end if that's all right.
That's fine. Just whatever you need, just ask for it and you'll get it.
You got it. Thank you.
Yep. All right. So here, let's talk about here's another kind. Here's another fourth. So I always think of categories. And again, what I think might be helpful to you is if you realize there's not an infinite number of categories. There's not an infinite number of problem types that you have to stress out about. There's actually quite a few. There's actually quite few. We just did a problem. We just did sort of a, I guess what I would call, we just did the following. We just used the, I guess what I term XY force table. We did a problem that really lent itself to this XY force table approach. So that's a problem category. Now you know, you've been introduced to that. Now we're going to do another basic category called ramp. And there's a ton of ramp problems. And ramp problems are good because they really do require you to break things apart methodically and then put them together in a certain way. So this is a ramp problem. And I'm going to remind myself of the recipe, the force analysis method, just to not lose track of this. Well, you know what I'll do? I'll just kind of unofficially roll it out. So here's the situation. You have a ramp, and this force right here is acting on the ramp. In fact, I redrew the whole thing over here because it's easier to see. So in fact, let me make that even a little bit bigger. This is a better picture. So when you do this methodology, there's like recipe items. So recipe number 1 is the free body diagram. So let's go ahead and draw the free body diagram for this object sitting on a ramp. And that's, I think, pretty straightforward. I have the normal force. The normal force is going straight up. This is the normal force. Normal force means perpendicular to the mutual contact surface. So I'm going to indicate that, yeah, this force is perpendicular. And I'm also going to indicate that, yes, this is right here. Let me do a different color. This is the shared contact surface right there. Okay. So, and again, this sounds very familiar. If you've reviewed the lecture video, please try to do that. And for all I know, every one of you has already given a good look at the lecture video, but I'm paranoid, and only the paranoid survive. Just because I'm paranoid doesn't mean you're not out to get me. So I'll just be repeating that every now and then. There's another force acting on this object called the weight force. So here's the weight. Weight force acts from the center of mass. So, all right, let's label that. This is mg. mg. This is F. That's normal force. Okay, done with the free body diagram. There's no friction, so I'm not going to worry about friction. Here's the next recipe item. Choose a coordinate system. Worry about the coordinate system. Here's what I'm going to do for my coordinate system. This is new and revolutionary thinking. I'm actually going to call the x-axis going up the ramp. So I'm actually rotating my coordinate system. Maybe I'll make it a little bit smaller. My x-axis is going up the ramp. My y-axis is perpendicular to the ramp. So again, I'm transforming, I'm rotating my coordinate system. This is y, this is x. And I'm doing that because my object is moving within that coordinate system. Now, here's the thing. I don't have to do that. I don't have to do it. In fact, you could make a case I shouldn't do it now, but I'm doing it now because it's pretty simple. It's good. This will be a good learning process. And it really does, I think, make life easier. So I'm done. I'm done with my coordinate system. I thoughtfully figured out what to do with my coordinate system. And then I need to decompose all 2D vectors. Decompose all two-dimensional vectors. That's kind of standard operating procedure anytime you have 2 or 3 dimensions. Just break them down. So I'm going to break down, I will break down this vector. All right, so for mg, here's mg's y component. Here's mg's x component. So let me just fine tune that just a bit. I want that to look like it's perpendicular because it should be perpendicular like that. Okay. So I'm going to label this. I've decomposed that two-dimensional vector. This is, I'm just going to call this mgy. M is a constant, but g, the acceleration due to gravity, definitely has a y component. And I'm going to call this mgx. Okay, and I know by definition, x and y are always perpendicular. So much, you guys, so many problems are solved just by getting yourself to a right-angled triangle. That's a big part of solving many problems, many problems. It's just find the right-angled triangle. And I have one. Here's a right-angled triangle. Now, check this out. My ramp angle is 25 degrees. Yours is probably something different. Mine is 25 degrees. So listen to my thought process I'm going to go through. If this angle theta is 25 degrees, watch the game I'm going to play. Here's the game I'm going to play. Well, if this is 25 degrees, I know this is 90 degrees. Not a great color. This is 90 degrees. And because I know a triangle has to have 180 degrees, I know this is 65 degrees. And let me just sanity check that. 25 degrees, which is my given ramp angle, plus 90, plus 65 better equal 180. And it does because there are 180 degrees in the triangle. So you know what that means? This angle right here that I'm indicating from here, this is a 90-degree angle. So that for sure is 90 degrees. So if I'm tracing out 90 degrees, and if this is 65 degrees, this angle right here has to be the same as theta, or 25 degrees. So that's how I do it. You can do it any way you want. But the bottom line is this angle theta here is the same as this angle theta right there. And I like that because that's my right angle triangle. All right, so I'm done decomposing that. I still have to decompose another vector. I still have another two-dimensional vector. It's this vector right here, my externally applied force. Here's the y component. That's my y component. This is my, oh, I drew that the wrong way. I'll start here. This is my x component. That's my x component. This is my y component. I'm going to move this out of the way. Let me just move my newfangled coordinate system out of the way.
Are you recording this lecture?
I assume so. I mean, you've been watching past lectures, right?
Yeah.
Yeah. So it's getting recorded. Okay. So that's that. Okay. So let me label this. Yeah, I am. I just checked. I am recording. Because then I just started to think about it. Am I recording? I'm recording by default. So just wanted to double check. So this is 90 degrees because by definition, x and y are perpendicular. This is fx. This is fy. And from an angle point of view, can you see that this angle theta here is going to be the same here? This is also theta. So I have theta appearing in three places. Theta is my ramp angle, which is given. Theta also turns out to be this triangle's angle right here. And you witnessed my explanation as to why. And it turns out this is the same theta here. So these thetas are all the same angle. This is why we study geometry, basically. Geometry and trigonometry. That's it. So I am done with my free body diagram. I'm done with my coordinate system. I decomposed all my vectors. Here's the next recipe item. The next recipe item is just to start applying Newton's second law. Apply Newton's second law. Apply Newton's second law as many times as needed. As many times as needed. So if you step back from everything we're doing, this whole chapter is about one thing, basically. It's about F equals MA. I mean, at the highest level. That's Newton's first law. It's also very much, this is Newton's second law, sorry. This is Newton's second law. It's also, it turns out, very much about Newton's third law, which is not to go into that too much now, but the force on object B from A is the same as the force on object A from B. We'll talk more about Newton's second law, but here's all we're going to do. Spending a lot of time with this meticulous setup, and you'll get really good at this with prep. With enough practice, you'll just be slicing through this quickly. But all of this was set up. Now, basically, let's start doing Newton's second law. All I want to do is just keep applying F equals MA. And I'm going to use something called an X force inventory. X force inventory, because I'm still sticking with these components. X force inventory, or XFI. XFI means X force inventory. let's add up all of the x forces. So sum up, let's sum up all of the x forces and deal with it. So I've got negative mgx plus fx. Those are my only two x dimension forces. And Newton's second law, again, over and over, I'm just going to keep saying F equals ma, F equals ma. So whatever the sum is of all of these forces right here, there's two of them here. There could be 16 of them, but whatever these forces are, they have to, at the end of the day, be equivalent to mass times acceleration. And again, I'm just making sure I'm clear on it. Yeah, I'm just going after the x components. So here's the next recipe item. Well, we got to, before we move on, let's keep hammering on this Newton's second law to see where it takes us. All right, negative mgx, I can write that as negative mg sine theta plus fx, and I can write fx as f cosine theta equals mass times acceleration equals 0, because a sub x equals 0, since the problem says the velocity is constant. So a sub x equals 0 because the velocity is constant. That doesn't mean it's motionless. In fact, it is moving, but it's moving at a constant velocity. So it doesn't speed up. It doesn't slow down. Let's talk about statement number 3. All right, so if I have a little sidebar conversation here, if I look at this triangle right here, this triangle, and I say, what is sine theta? Sine theta is opposite, which is mgx, all over the hypotenuse, over mg. So that's how I'm replacing mgx with this, mg sine theta equals mgx. So that's my x component. So now you know where this term comes from. And I had the negative. The negative, why is this negative? Because it's pointing in the negative x direction. According to my fancy new coordinate system, mgx is pointing in the negative direction. That's why that negative sign is there. And now you know why this is mg sine theta. Same conversation for this triangle. Let's take a look at this triangle right here. And you can see that I would say the cosine of that angle is side adjacent over hypotenuse, because I remember SOHCAHTOA. And that's why I can state fx equals f cos theta. And now you know why this term is here. And again, to repeat, it says this box, it's not motionless, it's moving, but it's moving at a constant speed. Constant speed means delta v equals 0. If the speed is constant, the acceleration is equal to 0. So no acceleration, but it is actually moving. So now what should we do? It's saying, what is the magnitude of f? Let's do a little sanity check here. Oh, actually, one of the recipe items, which I should draw your attention to, because you're going to do this, you apply Newton's second law as many times as possible, and then I should also say, you're going to always have to say something about acceleration. So let me be a little bit more careful here, because this is the methodology you're going to use. Apply Newton's second law, and then I would say here, make an acceleration statement. Say something or address acceleration. Okay, so here I need, right after the Newton's second law statement, which is basically, so I should have put it here. I should say maybe this is 2a. 2a, I really should have said something about acceleration, and this is where I should say acceleration equals 0 because the velocity is constant. So I'm done with that. It's cookie cutter, which is good. Cookie cutter is good because it lets you get to the moment of innovation sooner as opposed to later. All right, and then the other recipe item is just process. Or I'll just say process and repeat. Process and repeat as many times as necessary. As many times as necessary, as needed. Because my whole goal here, all I want out of life in the context of this problem, I just want a whole bunch of F equals MA equations. If I get enough F equal MA equations, I can solve them. So I might have Fx equals MAX, and then another F equals MA could be Fy equals MAY, and just keep going. Just keep cranking out F equal MA until you can solve. If I look at number 3, what do I know? I know mass, I know M, I know G, I know theta. This is my dollar sign. And I guess we're done. So we are done with part A as soon as you plug numbers in to the calculator. Okay. MG 78 times 9.8 times tan of 25. Oh, turn on the calculator. 78 times 9.8. Okay. So done. F equals 356.44 newtons. That's the answer to part A. So this is our very first result from our first ever force analysis method. Actually, second, if you count, we should count the first problem, that XY table. Okay, that's part A. Part B, what's the normal force so you know what? Let's look at Y. Let's do a Y force inventory. Let's look at a Y force inventory to find Fn. So here goes. Should be pretty smooth. Y force inventory means the sum of all Y forces. Now all you have to do, this is why your free body diagram is so important, because everything hinges on your free body diagram. I guess I erased F sub n. This was F sub n. So if I look at my Y dimension forces, I've got Fn going in the positive Y direction. I've got minus mgy. It's minus because it's going in the negative Y direction. Minus Fy equals mass times A sub Y. The very next thing you do is say something about acceleration. So let's address acceleration. Acceleration that always follows, your acceleration statement always follows your Newton's second law statement, A sub Y equals 0, since velocity is constant. Velocity is not equal to 0, but the change in velocity is equal to 0. So step number 8, solve for F sub n. So let's see, this will become F sub n, and it's trig time, F sub n minus mgy, so that will be mg cos theta minus Fy, and Fy is F sine theta equals 0. And let's just, again, a little sidebar here, just to be extra specific. I'm going to look at this triangle once again, this triangle, and I can see if I say cosine of theta equals side adjacent, which is mgy, over the hypotenuse, which is mg, which is why I'm writing mg subscript y equals mg cosine theta. So that's where this comes from. And it's negative because it's pointing downward. Going back one more time to this triangle right here, if I say, what's the cosine of theta for this triangle? The cosine of theta for this triangle equals the side adjacent, which is fx, over the hypotenuse, which is f. And that's why I'm saying fx can be written as f cos theta. So that's where this comes from. And it's negative because, again, it's going downward. Except, oop, mistake. Mistake. Let me erase this. I'm on the y force inventory. Yeah, I'm doing a y force inventory. So let me erase this. Very, very embarrassing. All right, so I need to do, I'm still on this triangle, but what I should have said, I should have said sine theta. Sine theta equals side opposite, which is Fy, over the hypotenuse, which is F. And now, correctly, Fy can be written as F sine theta. Okay. And again, that explains this. So hopefully I'm clear now about where this term comes from and this term, because F sub y is F sine theta and mgy is mg cos theta. And then let's solve. Let's solve for F sub n and be done with this problem. Number 9, F sub n equals, well, this is why I had to save F, so store alpha A. I'll indicate that here. Let's put this in memory location A, since I need to use it again. Store in calculator memory A times sine of 25 minus mg 78 times 9.8. Okay, 843 and some change. 843.42 newtons. This is the answer to part B. So this is our force analysis method, paying dividends. Bit of a learning curve, but it's going to be worth it. The alternative is not to have a methodology, and that is not feasible. So it is now 2:14. I'll see you guys at 2:21. It's daunting, but maybe not. Chapter 5, quiz 3. This is for sure calculus. I can tell right away. How do I know that so quickly? Because I can see there's a polynomial function right there. So this is for sure a job for calculus, which, again, to be honest, you guys, I said this before, there's not a ton of algebra. I'm sorry, there is a ton of algebra. There's not a ton of calculus, but there's enough so that you need to do it. And I mean, if you look back at chapter 2, chapter 2 was one-dimensional kinematics, but really more than anything, it was a sanity check. It was chapter 2 for me is me asking you, do you really know calculus? Which is why, and this happens every semester, why you get a huge drop-off in students. Like literally from the first week to the second week, a ton of students drop because this is an issue. A ton of students take this class really without having the right background math. So that's why you see like 25, 30, 35% or more students drop, because I try to make it super clear on day one that, hey, you know, you can't pretend to know calculus. You actually have to know calculus. So chapter 4 was really not much calculus at all. Chapter 4 was mostly, well, it was calculus and algebra. And a lot of you are finding, and this is true, it's true for me, a lot of you are finding that the calculus isn't so bad. It's the algebra that's the killer. And then chapter 5 from a math perspective, it's mostly algebra, but again, it's calculus and algebra. So there are some chapters that have very little calculus. Chapter 2, ironically, chapter 2 probably has more calculus than any other chapter, I think. And for physics 211, that's not true for physics 212, but again, it's good. I do like the fact, I do like starting with chapter 2 because for those students who just weren't where they needed to be for calculus, they drop the class. Then they come back, and they come back at some later date. Everyone wins. All right, and I'm thinking this is a job for calculus for one reason, that function right there. And I might be wrong, but at least that's my thought process. We have a 2 kilogram particle. So let's draw, this is two-dimensional motion. So this is y, this is x. So I have a 2 kilogram particle, which I will place right here. That's a 2 kilogram particle, 2 kg. And the velocity of this particle, this has so this is a velocity function, which once again, you as a scientist or engineer or computer engineer, you would actually program a device to give it this velocity. According to our statement, this has this, I could write this as, that's Vx. Let me just change my width here. So according to my function, this is Vx equals 3t I hat. Also, according to my function, my y component is 7t squared j hat. Let me go back to this width. Okay, so this would be Vy equals 7t squared j hat. And again, this is given to me. So the net velocity, in case I'm interested, maybe I will need to be interested, but there's the net velocity right here. So if I'm going to write this in vector form, I would say vector v equals Vx I hat plus Vy j hat equals 3t I hat meters per second plus 7t squared j hat meters per second squared. All right, so right, I don't even know what I'm doing other than I'm just setting up. I'm just visualizing my givens. 2 kilogram particle, that's my velocity function. At the instant the net force has a magnitude of 46 newtons, what's the direction of that force? All right, so that's the problem. For part A, part A is saying this, when the magnitude of the net force acting on that particle, when that magnitude equals 46 newtons, what's theta? What's the angle? That's the dollar sign. Theta is the dollar sign, the angle of the force when it has a magnitude of 46 newtons. So I could draw another, I should probably draw a whole nother, and you'll do this on the exam, you'll draw supplementary visuals like this. So I'm thinking, well, at some point, let's see. Let's just say, for the sake of conversation, I don't really know the true directions, but conversationally, this could be the x component of my force vector and the y component. So this would be the y component of the net force. This would be the x component of the net force. X and y are perpendicular by definition. So this would be my net force. First tail to last head. This is it. This is my net force. And right away, I'm thinking Pythagorean theorem, because that's a right angle triangle, which means you get to use SOHCAHTOA and Pythagorean theorem. So let's try to squeeze that out. Right now, I'm not seeing I'm not seeing the fourth. Well, here, this is theta. There's theta. So I guess I could say, well, I can see theta. Oh, let me back up. I could say tangent of theta equals Fy side opposite over side adjacent, SOHCAHTOA. So you know what that means. Here's theta. Theta equals arctan of Fy all over Fx. Okay, so are we done? Let's see. No, because I don't know Fy or Fx. So let's start worrying about those. Find Fx. Time to find Fx. I know this. Newton's second law says Fx equals m times ax. Generically speaking, F equals ma. Specifically for the x dimension, Fx equals max. Let's keep going with this. I know acceleration is dvx dt. So all I need to do is to take the time derivative of Vx. And I know Vx, this is Vx right here. So if I take the time derivative of Vx, that equals 3. But I'll do it like this. 3, what's the time derivative of 3t I hat meters per second? That's the okay. So number 4. All right, so here's Fx. Fx equals mass, which for me is 2 kilograms, times the derivative of 3t I hat meters per second is just going to be 3 meters per second squared, because this dt, when I have a dt in the denominator, that adds a dimension of time. So it's not meters per second, it's meters per second, but then I'm taking the time derivative, so I divide by seconds again. So that's how I do get meters per second squared in the I hat direction, and this is my answer. 6 kilograms times meters per second squared in the I hat direction equals 6 newtons in the I hat. And I'm done with Fx. So things, the sailing is smooth thus far. So let's just keep going and find Fy. Find Fy. Fy is Newton's second law says ma, and specifically m times a sub y. So it's just a copy and paste of what I did up there. M dvy dt, because dv dt is acceleration. And all I need to do now is take mass times the derivative of Vy, which for me is 7t squared j hat meters per second. And now this will be different because this result is Fy equals mass times, if I take the derivative of Vy, once again, this is my Vy expression right here. If I take that time derivative, it's 14t j hat meters per second. All right. So then here I'm going to write, trouble. And this is always going to happen. You're always going to run into these dead ends. And I'm saying there's trouble. What is t? What's t? So just expect dead ends like this. And now I got to find t. I must find t. Okay, so now this is where you get creative. This is where you look at all of the work you invested in the setup of this. And I'm going to look at force triangle, that force triangle that I drew there. That's catching my eye. And I'm not saying I see a path. I'm just saying, hey, It's something. So any port in a storm, you know, right now I'm grasping at straws, but I am looking at this triangle. And from this triangle, I can use Pythagorean theorem. So Pythagorean theorem here says f squared equals fx squared plus fy squared. So there's f sub y. Let's see where this takes us. So you know what I'm just going to do step number 9 right here. F squared is 46 newtons squared equals fx squared. Here was my fx right there equals fx squared. So I'm going to write down 6 newtons. I don't need to write down the I hat. Squared plus fy squared. Oh, and here's fy. Fy, I'm going to substitute in fy is going to be 14 times m. Let me do this here. I should have done this step here. This equals 2 kilograms. M for me is 2 kilograms times 14 meters per second times t. So I'm just going to write that as 28t. That'll be easier. So here, this equals, I'm just going to leave that as 28t. I'm going to maybe leave the units to the bitter end and just, that is again 28t. So now this is going to be just 28t squared. And as long as I'm not dragging along the units, I'll do the dimensional analysis again at the end. But I'm just going to say this is 6 squared. So, okay. Again, doing the dimensional analysis at the end. That's it. So I have 46 squared equals 6 squared plus 28t squared. All right. Yep.
If we knew f squared and fx squared, why couldn't we just plug those two in and just solve for fy as a variable instead of like making it the 28t squared?
If you solve for fy, maybe you're right there. Maybe you're on something there, because at the end of the day, we're just looking at these arctans. Okay, let me back up then. And let me take your advice. I was solving for time, and that might not be needed. So now what you're saying...
Just use the Pythagorean theorem just to find fy if you have the rest of the
Yep,
information.
just step number 9 would be fy equals f squared minus fx squared square root. Let's put that result in memory location A. Okay, let's do that. So f squared, for me, 46 squared minus 36 squared, square root of that. Okay, 28 and some change. 28.635 newtons. Okay. So I think you have a good idea there, Ali, because now I'm going to go back to, let's revisit number 2. Revisit number 2. Theta equals arctan of fy, which is sitting there in memory location A, all over fx, which is 6. And let's see, I divide this by 6, arctan, I get 78 and some change. Okay, so let me, 46 squared minus 36, right? Square root divided by 6, arctan. Okay, 82 and some change. 82.5 degrees. That's a good idea, Ali. This is 82.5 degrees going counterclockwise with respect to positive x-axis. It's that same convention again. So that is the answer to A. So congratulations to us. That is the direction of the force on this object when it happens to have a magnitude of 46 newtons or whatever your number is. Let's do part B. Part B is number 11. Part B is saying what is the net direction? What is the particle's direction of travel? Direction of travel. Particle's direction of travel. You know what that's referring to? This refers to velocity direction. Okay. That's what the direction. So really here's the theta now that we have to find. We have to find that theta. So from above graph, you can see that theta, once again, I can say is arctan of Vy over Vx. Okay. Do I know Vy? Yes, I do. So let's type in arctan of Vy. Here's Vy. For me, it's 7t squared. That's Vy. Here's Vx. Vx is 3t. Okay. That's that. That is that. And I just want to make sure we're not done, but I want to make sure I'm being clear. All right. Here is V subscript X. This is V subscript Y. That's a positive. Okay. And it's going to be 7t squared over 3t. That looks good. So then you can see I need to take the arctan of 7t over 3. And then you could, at this point, you could say, what's t? So this is where I guess we could go back and we're going to have to revisit. So we're going to do those steps, but now it makes sense to do these steps now. Look at.
Professor.
Yeah.
Sorry, I missed something. How'd you get 7t squared 3t to just 7t3?
Because
taking the derivative? Or something?
no, t squared cancels with t.
Ah, okay.
Right.
Okay,
Cancel simplification.
Yep.
Right.
Thanks.
Okay. So I need to find t. So I'm gonna look at force triangle. Mostly because that's all I got. Look at force triangle. Yeah, I just can't think of any alternatives. So
Also, for clarification, that 7t is now positive because of the direction it's going in, right?
it was always positive. Like here, if I erase this, see that?
Oh, okay. My problem, it was positive, but it looked like a minus for you. Sorry.
I know. I kept thinking that too, which is why I've done that a couple of times. I'm thinking the same thing. Right, but it is positive and it stays positive. All right, so if I look at this force triangle, which is the only other piece of evidence I can grasp onto, which is fair, Pythagorean theorem, f squared equals fy, well, fx squared plus Fy squared. And this is where I'm just going to stick with numbers. The magnitude of the force is 46 newtons. So this is 46 squared equals Fx. Fx was 6 newtons. So I'm going to square Fx. Yep. And Fy, did I write that down somewhere? Fy is right here. Fy is 28t. So Fy is 28t, and I squared that. Okay, so number 15, solve for t and store that in your calculator memory, and then we can solve. All right, so 46 squared minus 36. I get this for t, 1.62 and some change. 1.62 seconds and some change. I'm going to store that in calculator memory location A. So then I can be done. I'm going to revisit. Number 11. So here's the new number 11. Theta, the direction of travel, which is not the same as the direction of the force. The direction of travel is theta equals arctangent of 7/3 times A. And when I do that, there's A sitting there in my calculator times 7 divided by 3. Arctangent says 75 and some change, 75.25. 75.25 degrees. That is the answer to part B. All right. We're done. We're done. A lot going on. Heavy. This stuff seems really heavy only because it's your first look. Okay. And there aren't that many different categories. I'm basically throwing the entire variety of categories, and there aren't that many of them. You know, there's more than 2, but there's less than 1 million. So the number is between 2 and 1 million. There's a handful. There's like whatever, 6 or 7 or 8 basic problem types, and even then you can say, well, they're not really different types. They're all Newton's second law. All right, so that's quiz 3. Let me take a look at the grade book just to see. So you guys, you can't let this day pass without getting yourself full credit on all these quizzes, which means you're going to have to speak up. So 2 people are done with this quiz. Levi and Ty. Everyone else is done. Some people are really not done. So let me wait for a minute. I don't want to, even though I'm going to give you time on the back end, I don't want to go too fast. So, I mean, it's a delicate balance. I don't want to sit here forever, but I don't want to go too fast. Yeah, now we have Will and Ty and Levi and Ali are done. Some of you should be asking questions. So, for example, Locke, you should be asking questions. Jacob, Stuart, you should be asking questions because my guess is you're stuck. Alan and
Professor?
Lewis and Ethan and Leon, maybe you have questions, maybe you just need more time, but yeah.
It just says, could not submit answer. If error persists, you may contact support at Wiley Plus. Let me just try a random number.
It didn't time out. I don't think this quiz timed out. Is this the deal, Leon, where you have to maybe, are you still on a grace period? Because maybe your grace period, because Ali just said his grace period just expired.
Oh, maybe it's just, I'm just trying to answer B. I typed in the answer, but
yeah, and again,
that error.
One reason might be because your grace period literally expired like now.
So I should close out, right?
Let me see. I'm going to look. Maybe I can verify that for sure. If I can find that. I'm not seeing here. I'm
No,
not
it
seeing.
says 4:30.
No, it's your grace period. Like, did you purchase the Wiley Plus license, or did you sign up
Oh,
using the grace period?
I purchased it.
Did you? So that's not the issue. So that's not the issue, Leon. So did you try maybe going all the way out and coming back in and refreshing?
Yeah, that's what I'm doing right now.
Okay.
I'm sure I'll get a second.
Wait, what does the year say again?
It's can't submit answer. If error persists, contact Wiley Plus.
Did you finish quiz 2 and 1?
I finished 2, and I have one answer left on 1.
So I know one issue when I was doing the homework the other day that I found out not only applies to homework questions but also entire assignments. Sometimes if you don't complete previous assignments, you can encounter like bugs with the Wiley Plus that won't let you like submit answers until you're done with previous assignments. I don't know why it does that. It's kind of annoying, but
So how did you get around it?
I just had to go back and finish your earlier stuff.
Yeah. I wonder. Yeah, because I'm definitely, I mean, as far as I'm concerned, these are completely separate assignments. But what you said could be it. I mean, you might be right, although I don't know. Maybe that could be a bug. I guess we'll find out because Leon, yeah, you can, if you could, well, except here, Leon did not finish quiz 1, but he did finish quiz 2.
Quiz 2.
Right. So, I mean, I'm not saying that's not an issue. I'm saying I don't think that's the issue. I would just log all the way out and log in and restart. And then, to be honest, if that's still not working, man, go ahead and Wiley Plus is actually pretty responsive in real time in terms of their help. Because I can't think of, other than Will's suggestion, I can't think of anything to try other than literally logging off of Wiley Plus, logging in, and then getting back into things.
Okay, I'll work on that too. And then at the end of class,
One way or the other, you're going to get access.
Yeah.
I'm not going to run out of time. So, all right, so we can move on, even though, again, Locke, Jacob Says, and Stuart Horsewell, my guess is you guys have questions, but you're not asking them, which is fine. No one's forcing you to ask questions. So let's see here. Let me check. Here's an issue. Quentin Bruce, are you with us today, Quentin?
Yeah, I'm here.
You're not doing any of these quizzes.
Yeah, no. I honestly feel like I'm learning better when I go back and watch this lecture video and I can do it at my own pace.
That's good, except you're losing points.
No.
You're losing.
I'm trying to improve it.
That's fine. I mean, I hear what you're saying. I get what you're saying. It's just sit back and try. But here's the thing. These lectures are recorded. So you have the ability to rewatch these lectures many times over and over at your leisure. So why not do that? And in addition to doing that, get the right answers now. And there is benefit. If you kind of keep pace with me, there's going to be a benefit to that. It's going to make you just more, it's going to make you a better problem solver if you kind of try to keep pace. Now, anyway, that's my advice. Just up to you. That I just wanted to get some feedback from you.
Yeah, I hear you. Thank you.
Okay. All right. So then let's do the next quiz, which is chapter 5, quiz 4. Okay. So this is sort of another basic type, elevators. And you really could, you could argue that you could say, hey, Chris, there's not really this many types of problems because they're all sort of the same version of the same problem. That's just do force analysis method. Everything we're encountering is just a subset of the force analysis method, which is why I'm trying to really, spend a lot of time on the force analysis method. Because that is a good argument. You could say, yeah, you don't have to worry about categories. You just have to worry about methodology and approach. And all right, so this is, yep.
Just one kind of side question. It's not really that important, but I guess one question I have for like the test, questions we're going to see on the test, are those questions going to be similar to what we're doing
Yeah.
with the homework? And Okay. I didn't know if it was more about like, obviously like you want us to learn the material and like you want us to be comfortable with the homework, but on the other hand too, like I didn't know like how fresh it was going to be like on the test for you, making sure that we were comfortable with uh the processes that we're using like for the stuff.
Yeah.
Like what is, yeah.
Yeah. It's, I mean, to me, it's all about process and problem solving capability. There is a difference between process and problem solving capability, but this is the, I think, the ultimate readiness check. I'm just going to draw your attention here again. If you guys, and I'm going to shift my message a little bit. I think up until now, I was saying, hey, you know, this might be helpful. It might be helpful for you to use this traffic light report. And based on what I'm seeing, I need to change that message. So instead of me saying, you might want to look at this, it's pretty helpful, maybe, I need to say the following. You guys really need to use this. Again, I'm looking at quiz results. I'm looking at homework results. And this is helpful. It will be helpful if you guys say to yourself, I need to use this. I'm actually thinking of making this mandatory. So I'd like to make this mandatory, but I don't know how, because at the end of the day, it's going to be up to you to change everything from red to yellow to green. But again, I am seeing clear evidence that says you need to really do this. You need to change everything from red to yellow to green for all of the chapter 2 and 4 and 5 homework. You need to have full red, yellow, and green for the labs and sims. And again, if you don't know what red, yellow, green means, it's the descriptions here. You need to have full red, yellow, green for the lecture videos and green sheets. And at the end of the day, this is your review session. How do you know if you're really ready for this exam? Turn everything from red to yellow to green, and then you start solving random problems, which I will make available to you via Wiley Plus. So if you do all of the right things, everything's red, yellow, green, and you really digested this, you should be able to solve pretty much most, if not all, of these practice pool problems. Because as Will was asking about, the exam questions are going to be very consistent with the homework problems. And the homework problems are copy and paste versions of the quizzes. And this is what I'm talking about in terms of some Hall of Fame. So if you look at this problem that's on your screen right now, I created this problem from scratch, but I made sure it was consistent with at least one of the homework problems that you've digested. So there's step 1, there's step 2, there's step 3, and here's step 4. So again, I will make the following assertion. This problem is very consistent. It's not a copy and paste of the homework. Because if you're saying to yourself, I could see myself saying, why don't I just memorize the solutions? That's not going to work. You actually have to digest the solutions. But this is Rebecca's step 4 for this particular problem. And this particular problem is very consistent with the problem you saw on chapter 2. So just keep that in mind, because I do need to change my message. Because again, I can't help but notice statistics. And here's before we get back to the action, let me just throw this screen at you. Here's the other thing I need to start hyping very strongly. All right, so just let me go through this. You guys, you can't be late. Those of you who are arriving late, just stop it. Just that's not a professional thing to do. So just start taking the professional approach to classes, because the kind of student you are is going to be the kind of professional you're going to be. I mean, obviously, that's not 100% airtight, but just get in the habit now. Arrive early. I'm sorry. Don't arrive early. Arrive to every class on time. Don't skip a class. Man, I used to get myself in all sorts of trouble skipping. I skipped so many classes when I was in college. It was really quite ignorant of me. Here's one. This is what, again, Rebecca and I think Kevin, these are people from last semester. This is what a lot of students, I think most of the students did this. Check it out. you're gonna get full credit on all of these class quizzes. And after you're done getting full credit today or tomorrow, sometime today or sometime tomorrow, go right around and solve those same homework problems while it's fresh. So don't let things get stale. Here's another thing that this is, number 4 might be the biggest reason why I'm having this conversation. You guys, you just got to get out of the habit of starting homework on a deadline day. I saw that left and right. That can't work anymore. It's, again, treat it like a job. If you had a big proposal that you were making, you're not going to start the proposal the day of the deadline. You're going to do it in chunks along. So finish all homework problems before the deadline day. Complete. You guys should consider that traffic light report as mandatory, not optional. Always watch the Zoom lectures. Always watch the lecture videos before Zoom class. Always complete the green sheets before the classroom class. And here's what you should do. You should over-prepare for exam 1. You should spend like a ridiculous number of excessive hours preparing for exam 1. Easy for me to say, no, and then back off and then lighten up. Once you do really well on exam 1, then you can lighten up, because I know you have other things going on. I'm not ignorant to that fact, but it's going to be so much better if you make a really good first showing on exam 1 versus the alternative is you don't do well on exam 1. So you have to do well on exam 2, 3, and 4. And that's doable. Students do that all the time, but it's so much better if you can over prepare for exam 1. And usually what that means, it means quantity and quality. You guys need to spend enough hours to go from red to yellow to green, and quality means you really do have to spend these hours the right way. Really understand what it means to go from red to yellow to green. So wanted to throw that out there. Nice little break. But this is what I think you guys need to hear. I think you guys, you may not be familiar with classes at this level and above. This is not a high level class. This is a class that might be at a higher level than you're used to. And trust me, it gets much higher level than this. And you'll do it. You'll grow. You will grow with the degree of difficulty. And I think most of you kind of have to sort of kick yourself up a notch based on what I'm seeing thus far. So this is all meant to be constructive. My goal is to have you guys learn this stuff as deeply as possible. The end. Let's do chapter 5, quiz 4. It's an elevator problem. We have 2 elevator cabs. Elevators, again, a good thing to experiment with or to consider, because it's a pretty thought-provoking. The mass of this elevator, the mass of the top elevator is, for me, 1,600 kilograms. The mass of the bottom elevator, for my numbers, 1,390. So just doing the read through. They're connected by a cable. So this cable here, this cable might pull the elevators up or down. This is a cable. And it says right here, this is a 14 kilogram box of catnip. Catnip is basically ecstasy for cats, I think. I mean, I have cats. I don't give them illegal drugs, at least not publicly. But catnip is, I believe, some sort of stimulant for cats, I think. I don't know if it's a stimulant or a depressant, but we'll have to look that up. But the mass of this box is 14 grams, again, with my numbers. All right, and it's lying on the floor. The tension in the cable connecting the cap, so right here, this said this tension, so you would hook up a force gauge, and the force gauge would say this tension is 19,600 newtons. That's good. All right, that's it. What's the magnitude? So this is what we're looking for. What is the magnitude of the normal force acting on the catnip, acting on mass subscript C. So I'm just doing A, B, and C. This is, again, I'm referring to this as mass C. So let's do the recipe items. Job number 1, free body diagram. So I'm going to draw the catnip. Here's the box of catnip. Here's my catnip. That's MC. M subscript C. Here's free body diagram means I have to do my normal force. Here's the normal force. And technically speaking, the normal force is acting from the floor. So I'm purposely drawing the normal force as beginning at floor level. Here's another force, the weight force. And the weight force actually begins at the center of mass, is acting on the center of mass. So this is weight equals mcg. So you guys should know this for sure. Weight equals mass times gravity. And you would for sure know that, again, if you watch the lecture video. And so again, you guys, for sure by Tuesday, watch the lecture video at least once and have your green sheets done. Have your green sheets done by Thursday. Also by Thursday, you should finish all of the homework problems that are identical to the problems we're doing now. I'm not saying spend more time. I'm just saying whatever time you spend, I'm just saying spend your time earlier. Don't do it on a deadline day. Stay away from deadline days. All right. So that's it. So that's my free body diagram. What about the coordinate system? You always have to worry about that. Here's how I'm going to worry about my coordinate system. I'm not going to worry at all. I'm just going to stick with the standard up is plus y. I'm not going to worry about x. There's nothing going on in x. So I'm done with the free body diagram. Coordinate system decomposes the next recipe item, but there is nothing to decompose. So I'm done with decomposition because there are no 2D vectors. There's only one-dimensional vectors. My next item is basically, let's go ahead and do the X force inventory and or Y force inventory. And again, I don't have anything going on in X, so this will be a Y force inventory. And then after you do the inventory, say something about acceleration. And then go ahead and crunch time. And then rinse and repeat. Then you do the whole thing over again if you need to. Rinse and repeat if needed. And I'll need to do that. I'll need to rinse and repeat if I just don't have enough knowns, enough equations. So here goes. We are on now the Y force inventory because, again, there's no need for X. Sum of all those Y forces equals, let's see, I've got Fn going up and I've got mcg going down. Newton's second law says whatever the combination of forces is, no matter how many of them there may be, at the end of the day, it's mass of the catnip times acceleration. Okay, so the very next thing I have to do, I have to say something about acceleration. Because at the end of the day, F equals ma means you need to think hard about force, mass, and acceleration. So what can I say about acceleration? I can say poetically, I know nothing. I know nothing about acceleration. I know nothing about A. I know nothing about A. That's something. Okay. So I think that's where I'm going to probably start focusing because here's the result. If F, the normal force, this is my dollar sign. The normal force is equal to MC times A plus MC times G. And I'm just, where did I get that from? I'm just doing algebra right here. Okay. So in many ways, I've made lots of good progress because I can just say all I need to do is do A plus G. I know the mass of the catnip, that's given to me. I know G, that's 9.8 meters per second squared. Right now, this is what I don't know about. So this is It's the it's the moment that you will always have. All right, so what to do? Number 4. What tree can I bark up? Somehow I'm thinking I'm going to tap into this number. I'm going to tap into this number somehow because it's a number. It's a number. And I'm grasping for straws. I'm just trying to latch on to anything. I mean, if I said that a little more confidently, say, well, I'm just going to use the information that's available to me and synthesize the results. So this is what I'm going to do. Let's look at MB, which is the bottom elevator cab, M subscript B. Let's do a Y-force inventory. Do a Y-force inventory. All right, so number 5. Okay. All right, well, let's do free body. I need a free body diagram. That's job number 1. So here's elevator cab B. I'll draw it right here. This is M subscript B. I'm just redrawing it just to clear things. What are all the just to make it easier to read, what are all the forces acting on this? Well, there's tension force. Tension always pulls. Tension can never push. So I'm just going to call this is the tension force. I'll just call this T, the tension force between A and B. And now just a word about tension force. Even if this cable right here were lowering these 2 elevators, even if these 2 elevators were descending, this tension force would still be upward. So if these 2 elevators are rising, this tension force is upward. If these 2 elevators are descending, this tension is still upward. That's because tension can only pull. You can only pull a rope. You can't push a rope. So I just wanted to make that point. The other force acting on this is the weight force, which acts on the center of mass. So that's why I'm drawing it, acting on the center of mass. This is mass of elevator B times G, because W equals mg, courtesy of the lecture video and green sheet. So now let's do a Y-force inventory. Here goes. Sum of all of those Y forces acting on MB, I have TAB going up minus the weight force going down equals F equals MA. At the end of the day, F equals MA. Now, your very next step is to say something about acceleration. And here I can actually say something hopeful. So you got to follow this up with an acceleration comment. And then this is where you say, aha, the acceleration of elevator cab B is going to equal the acceleration of elevator cab A, which is that top cab. So I'm just going to call it A. Because, and you know why? Because mass B and, I'm sorry, mass A and mass B are connected. Are connected via a cable. So they move in unison. By a cable that's, I should add this, that's always under tension. You could actually make things complicated, or you could say, what if suddenly you lower? There might be some circumstances where this is slackened. So I'm going to make the stipulation here: always under tension. This rope is always under tension. Okay. So this is a big deal. This acceleration statement is huge because if I can find the acceleration here from step 5, then I am done with step 3. All right, so let's keep going with that. Step number 7 says TAB. Here's the value of TAB. So I'm going to process step number 5. If I start plugging in for number 5, TAB is 19,600 newtons minus MBG. The mass of B for me is 1390 kilograms times G. G is 9.8 meters per second squared equals the mass of CAD B, 1390 kg times A. So this is equation number 5 processed a bit. This is TAB. This is mass of B times G equals mass of B times A. So that is good, I think. Let's solve for A. Number 8, solve for A, acceleration. And then number 10, or step 9, I should say, go ahead and solve for F subscript N in step number 3. Okay, let's do that. I will do that too. That's that. Okay. All right. That's the answer I get. And this is only a single part problem. All right, so that's it. Let's see, it's now 3:18. I will see you at...
If anyone's there, is A the same thing as MCA? Like acceleration the same? Is he representing it the same as MCA in number 3?
For which one?
Like, wait, hang on. I think I'm saying this wrong. Just a second.
Oh, for quiz 4?
Yeah. Like, okay, we solved for A. You got A. And then you have to plug it back into number 3, but...
Yeah, so whatever you get for A's, you're plugging it back in number 3. Acceleration is going to be the same for both of those because they're both connected and both moving at the same speed, right? Ideally, so
Yeah. But
so
okay,
acceleration is going to be the same for both.
oh,
So do you have A?
yeah. How do I get MC or the mass of MC? How
So
do you get...
MC is just whatever the mass of. That's just whatever the mass of object C is. The box of catnip that's lying in the bottom of elevator A.
Oh, it's the same
You
number?
see what I'm saying?
No, I don't.
Yeah, that's. So if you go up where the problem statement is,
Yeah.
in the second line, there's a sentence that says a X kilogram box of catnip lies in the floor of cat A. Do you see that?
Yeah.
Okay, so that right there is the mass of C. That box of catnip is your mass of C.
Oh, okay.
Yes. So whatever that is going to be, you're going to take that and you're going to multiply that in step 3 by your acceleration that you got, and then G, which is 9.8.
Got it. Thank you. I appreciate it, man.
Okay. Time to start. We should be able to do one, maybe two more quizzes. Let me double check. We just did chapter 5, quiz 4. And now it's time. We're going to skip a number in the sequence and go to chapter 5, quiz 6. And we might back up and do chapter 5, quiz 5, but we are skipping a number in sequence. Going to chapter 5, quiz 6. Chapter 5, quiz 6. Yeah, this can go pretty quickly. Although I say that, it can go pretty quickly. On the other hand, I kind of go out of my way to draw this out as much as possible, just to really do the deep dive into the bowels of all of the conceptual underpinnings and problem-solving tactics. So the goal is to never move quickly. Having said that, though, relatively speaking, this shouldn't take too much time. Okay. Let's get started. This is called, this looks like, this is the elevator machine. So this is basically an elevator device, known as the Atwood machine. And you can see it does look kind of like an elevator. One cab is going down while the other cab is going up. Atwood machine is what's being visualized here. Let's do the read through. This says the figure shows two blocks connected by a cord of negligible mass. And that's, I guess, important to know. Well, I don't guess that is important to know. Okay. We have a pulley. This negligible mass cord passes over a pulley, connects M1 and M2 as shown. The arrangement is known as the Atwood machine. Block 1, we know the mass of block 1. We know the mass of block 2. What's the acceleration? What's the tension in the cord? All right, so this is a pulley problem. So there are pulley problems. There are ramp problems. There are XY force table problems. What was number 4? Number 4 was an elevator problem. So now, and there's a few, and these are on your green sheets. I kind of summarized the basic problem types in your calculator. But again, you really could argue that that's not too enlightened, because you could make a strong case, for example, that a pulley problem and an elevator problem are very, very similar. And then you could also say, well, everything we do could be fit into an XY force table. So that's why I'm saying there's not an infinite number of weird types of problems that you have to worry if you basically get the big picture. So we have to find the acceleration and the tension in the cord. Here's my force analysis method recipe. First things first, free body diagram. FBD, free body diagram. So I have two bodies. So when I say body, I have two bodies. So this is tension going up. This is tension going up. This is weight coming down for M1. For M2, this is tension going up. And this is weight coming down. And I better label this stuff. This is, I'm going to call this tension acting on block 1. This is weight equals M1G. Weight equals mg. Similarly, for M2, I have tension pulling upward on block 2, and I have the weight pulling down on block 2, which is M2 times G. So I'm done with the free body diagram. What's next? What's next is coordinate system. And now check out my coordinate system. I'm going to do this for my coordinate system. I'm going to have two different coordinate systems. I know for a fact, and so here's sort of the cue you look for. Do you know the direction of acceleration? And the answer is, yeah, I do know. I do know the acceleration of both of these masses because M2 in my case, M2 is greater than M1. So the direction of the acceleration is going to be downward. So I'm going to take advantage of it. I'm going to call this plus y. So everyone's accustomed to plus y pointing upward. I'm going to call plus y downward because I do know the acceleration of mass 2. And similarly, because they're connected via that rope or this cable, I do know the acceleration of mass 1. So let the acceleration guide you in your selection of coordinate systems. And I need to say that a whole bunch of times because I don't think it's the world's most sophisticated thing, but it's easy to not take serious. I'm going to say use acceleration as a guide, which I did. And then another big requirement is consistent. Establish consistency across all objects. I'll just say established consistency. And this is what I mean. First of all, let's talk about using acceleration as a guide. I explained it once. I just want to go over it again. I do, in fact, know the direction of acceleration because M2 is greater than M1. Maybe it's the opposite for you, but because M2 is greater than M1, for sure, this is going to accelerate downward. And for sure, this is going to accelerate upward. So that's me tapping into what I know about acceleration. Are they consistent? And the question, the answer is yes, they are consistent because the acceleration of mass 1 is in the same direction, is consistent. It's not in the same direction, is consistent with the acceleration of mass 2. And again, I'm saying that because if mass 2 is accelerating downward, then mass 1 has to be accelerating upward. So that's consistent. Alternatively, you could say if mass 2 were accelerating upward, then mass 1 would have to be accelerating downward. So that's what I mean by consistent. I mean, imagine this. Can you imagine a scenario where mass 2 accelerates downward and mass 1 also accelerates downward? No, you can't. The cable wouldn't allow that to happen. So that's what I mean by this term consistent. So I always have to be consistent. Like what if I don't know? What if acceleration is unknown? Acceleration direction is unknown, which is probably going to be more often the case than not. What if acceleration direction is unknown? And the answer is just establish one. Just take a stab at it. Just take an arbitrary stab at it. As long as it's consistent. So make sure whatever you do, it's consistent, and hopefully you understand what consistent means. Block 2 cannot move down while block 1 is also moving down. That would be inconsistent. So there you go. That's the coordinate system. That's a big subtopic to cover. We have to next worry about decompose all 2D vectors, but there aren't any two-dimensional vectors. But we're going to make a list of it this time. Decompose all 2D vectors. And we're done with that because there are no 2D vectors. What's next? What's next is the X force and or Y force inventory. So now let's do X force and or Y force inventories. Then the next thing you're going to do after that is talk about acceleration, and then crunch, and then rinse and repeat. Rinse and repeat. Over and over until you get enough F equals MA equations to solve. All right, so I'm right here, number one. Number one, let's do the Y force inventory. Let's do the Y force inventory for M1. Okay, here goes. For M1, my Y force inventory, let's see.
According to Wikipedia, the Apple app.
Google's listening to me. Google's eavesdropping. Big tech is on my case. All right, so for M1, I've got T1 going upward, so that's positive. I've got M1G going downward. Newton's second law says F equals MA. So there it is. That's my Y force inventory. Next thing, make a statement about acceleration. And aha, I can say a lot about acceleration. Acceleration is a dollar sign. And I can say, not only is it a dollar sign, the acceleration of object 1 is equal to the acceleration of object 2. And I'm just going to call that A. Why is that? Because I have consistent coordinate systems. Consistent coordinate systems. And on top of that, and what else do I have? It's string. They're connected. It's the same rope. Both connected to same cable. That's why. That's why I can say what I'm saying here for my acceleration statement. Number 3, I'll go over here. Let's crunch it then. Can I can't say anything. That's, well, I could say this. Well, I can say one other thing. I'm going to say the tension acting on object 1 is the same as the tension acting on object 2. So let's just call that T, because once again, it's the same cable. I only have a single cable connecting M1 and M2. So anywhere within this cable, anywhere I take a tension measurement in that cable, it's going to have the same reading, same result, because it's a single cable that connects M1 and M2. So here's my final result. I have T minus M1G equals M1 times A. And there are my dollar signs. T is a dollar sign. A is a dollar sign. So I need another. I can't solve that. I have one equation with 2 unknowns. So not to fear. Let's go ahead. Let's look at M2. Let's get another Newton's second law equation from M2. So I'm going to do a Y force inventory for M2. It's Y force inventory time. So here goes. I have negative T2, because that's going in the negative Y direction. I have positive M2G, which is the weight. That equals, I should do, let me back up. I want to do this. The sum of all of those Y forces acting on M2 is negative T2 plus M2G. Those are all of my forces. What does it equal? MA. Mass of 2 times A of 2. And then say something about acceleration. And I've already said something about acceleration. I'm going to say something. I'm going to say the same thing just for reinforcement. Whatever the acceleration of 1 is the same as the acceleration of cab number 2. So let's just call it A, and the explanation is right here and here. Okay, and then I'm remembering that T1 equals T2. So let's just call it T because it's the same cable attached to both objects, same tension everywhere in that cable. So this is my second Newton's second law, minus T plus M2G equals M2A. So I have two equations. I have two Newton's second law. Here's Newton's second law for M2 in the y dimension. Here's Newton's second law for mass 1 in the y direction. Let's solve these simultaneously. So this is how I would do it. So this is the algebra. And again, I don't know for sure if this is true with you guys, but I know from experience a lot of people get lost right now. That they never really get lost with the calculus, but they get lost on the algebra. So I'm going to do this. I'm going to add, I am literally going to add equation number 4 and equation number 9. So when I do that, this is just my technique. You can do something else, but here's equation 4. T minus M1G equals M1A. Here's equation number 9. Minus T plus M2G equals M2A. And like I said, I'm adding these equations. So this is how I think about it. I am adding the left sides and I'm adding the right sides. So if I add both of these equations together, I'm going to get M2G minus M1G equals M1A plus M2A. So at this point, solve for A. And then you're going to get the right answer. Once you solve for A, then solve for T via number 4, via equation number 4 or number 9. You choose, up to you. Okay, let's do that and we'll be done with this problem.
Did you have to add those equations together to find A?
No, you can do whatever you want.
Or is there another way you can find A?
Yeah, whatever your preference is. That's just a way. It's my way. It's not your way, unless it's coincidentally your way. All right, so we're solving for A. T equals all right. We have time for one more quiz, so I'll set that up while you guys are still hammering away on this one. Quiz 5. Hang on, let me interrupt this. Sorry for the interruption, but quiz 5 is problem 50.
Uh,
This will be our last quiz. Let me just say this again, you guys. Sometime today or sometime tomorrow, go right into your homework and solve all of these quiz questions that exist in your homework. Just sooner is going to be better than later.
hey, Professor.
Yep.
I'm trying to figure out if you'd be able to help crunch some numbers, on my end. For some reason, it's not coming up as correct on Wiley Plus, even though.
All right. Let's see. Okay. So I'm going to get from all of this. Let's see here. If I crunch all of this, this is going to be A equals M2 minus M1 times G over M2 plus M1. Did you get an expression like that?
Yes, just make sure
All
I
right.
have that right.
All right. So what was your M2?
All right, so M2 was 2.3.
2.3. What was your M1?
It was 1.
1.
Yes, just 1. Exactly, yeah.
Just 1. All right. Over. So then M2 plus M1 is 2.3 plus 1 times 9.8. So your acceleration should be 1.3 times 9.8 divided by 3.3 or 3.86.
Yeah, it should come up as 3.86.
And was that marked wrong?
Yeah, it was marked wrong, yeah.
Huh. Okay. Well, because if you get that wrong, you're going to get the tension wrong. Well, I could see if you took the opposite approach, but let me take a look in your grade book. This was for chapter 5 quiz. This was quiz 6. Okay. Chapter 5 quiz 6 is right here. All right. Okay. For you, I get different numbers for your I get different number for your masses. I get mass 1 is 2.5 and mass 2 is 4.
Nope, that's not on mine. Yeah, mine only says block 1 is 1 kilogram and block 2 is 2.3 kilograms. So it's weird because the tension came up right when I did the equation. So acceleration is right, the 3.806, but
Yeah.
it's not coming up right in Wiley Plus. So I got the tension right when I plugged A in to get T, but
Right.
A
So you
itself,
got part B correct. Is that right?
yes.
Yeah, and there's no way you can get part B correct and not part A. So let me come back and look at it then, because maybe I'm not, because again, I'm seeing different numbers and I must not be looking at the right area. So let's circle back on that. But your grade is reflected. You're basically, if I look at your grade book for chapter 5 quiz 6, yeah, you got about half of it right. So okay, let me come back to that then, because that's weird.
Yeah, okay, thank you.
Yep, for sure. All right, so let's do chapter 5 quiz 5, and this will be the last quiz we do today. Chapter 5 quiz 5 looks kind of weird, but actually there's not a lot there. So okay, it looks pretty messy, but this is not a new problem. So I think I don't think we're completely done. But we're getting pretty close to being done with the basic kinds of problems. Okay, so here we have It's another pulley problem. So this is definitely in the realm of pulley problems. We have 3 ballot boxes. So election intrigue. In the figure here, 3 ballot boxes are connected by cords, one of which wraps over a pulley having negligible friction on its axle and negligible masses. We know the mass of A, B, and C. When you release these things from rest, what's the tension in the cord between A and B? I'm sorry, between B and C. All right, let's just start with the force analysis method. Step number 1, free body diagram. Okay, so here's mass A. What are the forces acting on A? Well, there's this tension force. So I'm saying this is the tension acting on A. There's also a normal force, has to be. Normal force technically originates at the tabletop. So this is the normal force. And there's the weight force. The weight force initiates at the center of mass right about here. And again, that is the weight of mass A times G. That's it. There's no friction. We'll deal with friction in chapter 6. So chapter 6 is just like chapter 5, except we introduce friction and centripetal motion. This is it for mass A. Got it. Free body diagram, coordinate system. So this is where you ask yourself, do you know anything about acceleration? And yes, I can say one thing for sure. If there's an acceleration, then the acceleration has to be in that direction for mass A, and it has to be in this direction for B and C. So I'm going to use that. I'm going to use that knowledge of acceleration. And if you didn't know it, you would just guess. I'm going to guess it's that way. All right. So this is it. I'm going to call this plus X. This is that's my coordinate system. Do I have to decompose anything? No. So this is decomposition is done. There are no two-dimensional vectors. And now it's time for an X force inventory and or a Y force inventory. And then say something about A and then crunch and repeat. Okay, so hopefully getting pretty comfortable with this process. All right, so I guess I'm ready. Now I've done all of that stuff. Now I'm going to do an X force inventory. Here's my X force inventory. TA, that's it. There's only one X dimension force acting on block A. TA equals, that's it, equals the mass of block A times the acceleration of block A. Number 2, say something about acceleration. The acceleration of block A is going to be equal to the acceleration of block B, and that's going to be equal to the acceleration of block C, because you see they're all connected, and I have to have the coordinate system set up the right way. So let's just call it A, acceleration A. Okay, and while I'm here, I can see that the tension force acting on block A is going to be is the same as the tension force acting on block B, because that's the same strain. All right, so just throwing that out there now, because now I can say this. The X force inventory for block A yields this. T equals mass of A times A. Okay. We need to find out what's the tension. So that doesn't help us at all. It doesn't help us now, but maybe it will. Anyway, that's the result of an X force inventory for A. Let's just keep going. What about, let's do a Y force inventory. The Y force inventory for block A, this is going to be really easy. The sum, and I should have said this. I should have said the sum of all X forces equals that. The sum of all Y forces, well, I have Fn going up I've got the weight pulling me down. It equals ma times a. And say something about acceleration. A equals 0. There's no plus or minus y motion. Block A is just sitting there on that tabletop. It's moving along the tabletop, but it's not moving up or down. It's just moving left and right. So then here's the result. I can say the normal force equals the weight force. Again, not sure that's going to help, but I'm just gathering ammunition. That's the result of my X force and Y force inventory. I am after, when the assembly is released from rest, what's the tension in the cord connecting BC? So now I guess I'm going to get to that. So I'm going to see my dollar sign for the first time, because I'm going to do a force inventory on block B. So here's block B. Block B will look like this. Let's do block B. Is sitting here. That's block B. Okay. Block B. What are the forces acting on block B? There's tension force going upward. Like that. So this is T. This is the tension force pulling up on B. And again, this tension force would be upward, even if block B was descending or if it were ascending. It doesn't matter if block B is moving vertically down or vertically up. The tension force is always going to be upward. And we said, based on the previous statement, that tension B acting upward is the same as the tension in A, and we're just going to call that T. Okay. Are there any other forces acting on block B? Yes, there are. There's another tension force right here. Tension force is pulling down. Okay, so this would be T BC equals dollar sign. When the assembly is released from rest, what is the tension in the cord connecting B and C? So that's our dollar sign. Good to know. There are no more forces acting on mass B. So let's go ahead and do our Y force inventory. Number 7. It's the Y force inventory for block B, which is basically saying, let's add up all of the Y forces. And, okay, I have tension. Oh, I got to worry about a coordinate system. Oh, that was close. That was close. Here's my coordinate system. 1 second. Okay. So I need to establish, and to be consistent, I need to call this coordinate system downward. I know there's going to be a downward acceleration. So you guys have to be clear on that. Make sure we talk about it. If you're not sure why I'm calling downward plus Y, let's talk. So you have to understand why I'm calling that plus X, why I'm calling that plus Y. If that's plus X, this has to be plus Y. All right, so with that said, my Y force inventory is then going to be negative T plus TBC equals mass of B times A. And you follow that up robotically with an acceleration statement. Once again, the acceleration of A equals the acceleration of B equals A, the acceleration of C. And we're just going to call them all A because, as mentioned, you're looking at the same string, and you're looking at, I should add this, and you're looking at consistent coordinate systems. All these coordinate systems are working together, consistent coordinate systems. They're all kind of moving in unison. So here's my Y force inventory for block B. Number 9, I have minus T plus TB, well, I guess I'm saying nothing new, plus TBC. I am saying nothing new, equals M sub B. All right, so anyway, this is it. This is yet another Newton's second law equation, which makes you feel good because it's just ammunition. There's my dollar sign. There's my dollar sign, but I don't know anything else. So that's fine. Okay, let's do one more Y force inventory just because I'm just taking advantage. I'm just using what I'm being given. So let's do a Y force inventory for mass C, which means it's free body diagram time. Here's mass C. This is mass C right here. Here are my forces acting on mass C. I have the upward pull of tension. Tension is pulling up, and this is, in fact, it's the same. It's the same TBC, which is that same dollar sign. I have the weight force pulling downward on the center of mass, and this is mass of C times G. That's it for my free body diagram. My coordinate system is downward. I got to be consistent. So this is plus Y. Let's do the Y force inventory. I have sum of all Y forces equals, I've got negative TBC, negative TBC. So I've dealt with that. And then I have positive plus MCG, and I can see I made a mistake somewhere, but but let me keep going here. Step 11, I have negative TBC is going in the negative Y direction. MCG is going in the positive Y direction. That's it. This equals F equals MA. Here's F equals MA. Done with that. For the third time, acceleration on block A is the same as B and C, and we're just calling it A. All right, so number 13, this is what I get. Negative TBC, yeah, plus MCG, again, nothing new here, equals MCA, and that's it. And now I have to go back and I think fix a mistake I made. I'm going to go back to mass of B, my free body diagram, because as I look at mass B, yes, I have TB, so this is TB, and it equals TA, yes, and we're just calling that T. But downward, I'm just, forget block C. For block B, I actually have the downward pull of tension. You know what I forgot? I forgot the weight of block B. So I need to go back up here to step 7 and do a little bit of erasing. So for block B, I have negative T plus TBC plus the weight force. This is plus mass of B. The weight of block B equals mass times acceleration. And let me just add that to this visual here as well. Tension is pulling the block down and the weight, MBG. Okay. Which means I need to update number 9. So here's the update to number 9. Minus T plus TBC. Plus MBG equals MBA. All right, so I have all of these equations. At this point, I'm going to solve. And if I can't solve, I just got to figure out some way to crank out some more equations. All right, so I'm going to look specifically at this equation, minus t. Okay, I'm going to look at this equation as well. So I got to throw these three equations into the blender and get the right answer. So here's a, again, you can do this however you want. This is just a way. It's not the way. It's just my one approach. All right. So, well, I'm going to make this substitution right here. I can see that this minus t can be replaced with that. So if I, here's my new number 9. Here's my new number 9 is going to be minus mass A times A, because that's equivalent to T, plus TBC, which is my dollar sign, plus MBG equals MBA. So this is a combination of number 3 and number 9. And then right below it, I have number 13. So here's step number 13. Step number 13 says minus T BC plus MCG equals MCA. And then you're done. You're done. So go ahead and take these two equations, and from these two equations, solve for A, and then solve for TBC. Isn't that what we're doing? Oh, no, it's not. Right now, we're just saying solve for tension. So let's see. We have some more work ahead of us. I almost cut us off too soon. So solve for A. Okay. When I solve for A, let's all solve for A. A equals
If you don't know A, how are you solving for, or sorry, if you don't know tension BC, how are you solving for A?
step 14. You have two equations. So solve these two equations. You have this equation and this equation. So blend them, use your algebra and find acceleration. Okay. So that's going to be MB plus MB is 41 plus 9.8. That looks good. Divided by 31. Acceleration for me equals 6.1833 meters per second squared. I'm going to store that in calculator memory location A. I'm just going to repeat it just for the double check. Okay. MAA. Except no, this is good. Okay. What's the tension? Shrink.
Are you still looking for the tension?
No. Now we're going to move on to part B. As soon as we get, Well, to get tension, we need acceleration. Then we need to do kinematics for part B. But I just need to double check my results here. I'm going to deal with those two simultaneous equations in step 14, and you can see how you can just add them together. All right, so this will be MB is 41 plus MC is 12 times 9.8 divided by okay, I'm getting the same number twice. So that's a good sign. Now that we know acceleration, find TAB from number 13. That looks short. So number 13 says TBC equals MCG minus MCA equals MC times G minus A. Is that right? MCG. That looks good. And I know what A is. Times MC 43.4. Okay. This is the answer to part A. And the only way I could get this answer is if I got my acceleration. And for part B, they actually want you to do kinematics. Part B says, how far does the block move in the first 0.25 seconds, assuming everything's frictionless and it doesn't reach the pulley, and it's starting from rest, release from rest. So you know what? This is a job for Y initial, Y final, VY initial, VY final, A sub Y, and T. Yes, it's a job for the 6-column data table, the kinematics analysis method. Y initial, it says how far does block A move? Actually, I need to change that, X. So this is X initial, X final, because they're talking about block A. This is VX initial, VX final, A sub X, and T. Because again, they're asking about block A. So this would be, well, I'm going to say it's going to start from 0 meters. It's going, X sub F is the $sign. How far does it travel in the first 0.25 seconds? It's starting from rest, so this is 0 meters per second. The final velocities I don't know, and I might not care. A is whatever I have here in memory location A. Do I still have that? Yes, I've stored that acceleration value, and T is 0.25 seconds. So what a great problem, just because it's force analysis and kinematics analysis. And I just need to do kinematics analysis method right now. And when I do that, I am seeing, I'm going to guess the following. Step, I guess I'll call this 18. Step 19, I'm going to guess this. Guess X final equals X initial plus VX initial times time plus 1/2 A sub X T squared. So with numbers, X initial is equal to 0. VX initial is equal to 0. So here's my answer. 1/2 times the acceleration, which is sitting there in memory location A, times T squared, for me, 0.25 seconds squared. And so the answer there is times 0.25 squared divided by 2. 0.19 and some change. That's the answer to part B. And that concludes we did 6 quizzes today. It's now 4:18. We just did 6 quizzes. Is that right? That is right. So you know what I'm going to do? I'm going to extend the deadline for all 6 quizzes until 5:30. So you guys have between now and 5:30 p.m. to finish all 6 of these quizzes. Let me know if you need more time, and let me know if you have any specific questions. And let me just, once again, before I sign off, again, I'm going to hang out here. I'm going to hang out here just for a moment, and while I'm hanging out, you can drop off whenever you want, because you know that I'm going to take the next few minutes to extend all of these quizzes until 5:30.
Hey, Professor.
Yep.
So I had 2 questions for you. The first one was, were you able to give me credit for that quiz 6 for part A?
I figured we'd come back and look at that.
Okay, all right.
Let me just take another look. Otherwise, yeah, I'll just give you the credit.
Okay, real quick, for this problem, so how many total steps? We had, what, 18 steps? Couldn't you have just saved yourself time if you had used the F equals ma equation to find your acceleration faster?
Maybe. All I'm saying is that whatever you do, just make sure you follow all of those force analysis checkboxes. So my goal, when I do these problems, my goal is not to find the shortest path to the answer. My goal is to provide, I guess, the full scale, broken down into baby steps solution. So that's not to say you can do the same thing in a shorter way, but yeah, you can solve it however you want, but you have to use the force analysis method in its entirety.
I mean, I would just, I was looking at this because I was trying to figure out, like, I mean, we did looking at, like, each of the different masses that we had for A and B on this one. You have 2 different body diagrams, which kind of makes sense if you're doing, like, the free body stuff.
Right.
But, like, for me, what I did, I just added up all the masses that we had, and then you have
Right. I know that
all your forces, yeah.
You would,
Yeah.
I know that approach. I was taught that approach. The approach that I took you through today is better. So, I mean,
Okay.
I'm glad you brought that up. If you did what you say you did on the exam, you would get 0 credit because you have to use the methods that are taught, because the methods are taught might be a bit overkill for simple problems, but they're going to be essential for more advanced problems. So you need to do 2 things. You need to get the right answer, and you need to adhere to the methodology.
Okay.
So that's what I'm saying. I know what you're saying. I could have solved this problem using your approach in literally 5 minutes. I know I could have. So, but that's not the purpose here.
Yeah, I gotcha.
Okay.
All right.
Good. Thank you.